let's get to the tasks. We already saw what a task is. It is a C function. The C function has got some initialization code, and then it runs in a never-ending loop. You can see the prototype of the task. It's a void task because it never returns. It doesn't have any place where to return. And it gets a argument that's a void constant pointer. So you can pass any pointer to anything. Typically, it's an initialization value. It can be a number typecasted to a void pointer, or it can be a pointer to a structure. Very often, it's null. But if you, for example, instantiate several tasks using the same function, this typically gives them an idea which task it is. So it can be a different TCP IP port. It can be the number of the task if it matters for debugging purposes or for communication purposes. So the argument is the initial argument that's called when you create the task. And when it's executed, it gets passed as an argument. Each task has its own stack, priority, state, where it can reside, and it is created by a function osThread_create, and it's deleted if you call osThread_delete. Which means if you have a task for one purpose, you can instantiate it, it gets executed, and it can delete itself. When all the initialization is finished, why should I keep it in the memory and in the lists? I just remove it, and it's never scheduled again. Task consists of a couple of elements. The first one is the program code. When you create a task, you put a name of the function of the task into its definition. So it's a pointer where the scheduler should jump when it starts this task. And it calls the code of the task, the routine, and that's why we need it in a memory. Then it contains the stack where it holds its local variables. And it has got the TCB where FreeRTOS stores the data, the context, and the state of this task. A very interesting thing, the TCB, you don't get a pointer to it. What you get pointer to is the top of the stack. So if you want to see the TCB, you have to take this pointer, the original pointer, and decrement it by size of the TCB, because the TCB is below. When you create a task, PV port malloc is called, and it creates in the FreeRTOS heap the space for the stack and for the TCB. So the first creates the TCB, second allocates the task stack, and both values are saved in the TCB itself. When you do a switch from one task to the other, it's called context switching, and effectively the context, the registers, are stored in the TCB, and the new task restores the registers from its own TCB, and then it's switched to. And here you can see an example of a task function. So we define it as a void function because we don't expect any return, a name of the task with a prototype for the argument. Then we can run an initialization code. For example, if this one is responsible for speaking to the Bluetooth Low Energy coprocessor, we can instantiate and initialize the UART. Then in the loop, we can care about the communication with the BLE. And we should never get after the while one loop, because we don't have anywhere to return. So such block should not return anywhere. If you want to stop this task, you can suspend it or you can delete it, but never exit the function. We can see the state machine, how the tasks can operate. So when they are created in a ready state. And when the scheduler decides to execute it, it gets to the running state. And from running, it can get again into the ready by yielding, and it can get as well to the blocked state by waiting for some resource or for a timeout. And it can be as well suspended, and effectively it can be suspended from any of the other tasks. When it gets resumed, it gets back to the ready state by OS thread resume. You can as well suspend all tasks if you want, and you can resume them by an interrupt. The thread state, it can be obtained by a CMSys function to get the state of the thread, and you can see that all can be decoded. The task priorities are defined as a number from 0 to the max priorities -1, and the execution of each task is dependent on the priority. Remember that the number of priorities as well defines the number of the lists in the ready state. So the more priorities you define, the more memory it will request, which means limit the number of priorities only to the needed ones. The priority can be changed in runtime. So if you know that a task that is normally dormant will be needed in the near future, you can boost its priority temporarily, and when the job is finished, you can reduce it again. So playing with priorities is a good trick how to increase temporarily importance of some communication or some process, and then you can again reduce the priority, or you can put the task in a suspend. There exist some system-defined priorities. You can see them like starting with the idle priority with a value -3. Then we have got low, below normal, and normal priorities up to 0. And we can as well increase the priorities up to the real time with a value 3. Then, of course, you can define your own set of priorities. There is as well a special value OS priority error. On this slide, you can see how the two different strategies cooperate among the tasks. So when the task switch occurs, when the state of the tasks change. And you can see that with the preemptive mode, there is much more task switches, so it takes a little bit more CPU resources. You should remember that the tasks are organized in the lists. The list can be, or definition can be obtained in this header file. You can see what is implemented inside each list. So there is a test value to validate whether the list is not overwritten. We have got a priority, we have got a pointer to the sequential items. We have got a mini-list item, and again an integrity value to test whether the list is fine and wasn't overwritten. When we speak about the context switching, we can see step by step what happens when we get a source for the context switching from the sysdig. First, we get a sysdig interrupt that causes the execution of export sysdig handler. This is implemented in port C, and it's normally written in assembly to be effective, and it depends on the architecture. So for Cortex M0, it will be different from Cortex M3 or M4. This interrupt handler will first disable all interrupts. This is to block any other system functions to interfere or interrupts to call any system functions. Then it activates the pendable SV bit so that at the end we will execute the context switch when the sysdig handler is finished. When the context switch will happen after we enable the interrupts again at the end of the function, the pendsv will call the task switch context, and this will call the macro select the highest priority task, which goes through all the listed ready tasks and chooses the one with the highest priority put at the beginning of a given list. Then when it is executed, it's put at the end of the list. So it always rotates. So when the SysTick handler enables the interrupts again, the pendable SV is executed physically and the task switch occurs. So, switching time depends on the interrupt latency, and on Cortex-M is somehow fixed. So, there were some test conditions, like it was compiled by Kyle for Cortex-M3. The stack overflow checking was turned off to show just the pure context switching. The compiler optimization was set for the speed. And there was as well a macro port optimized task selection enabled. So with these compilation setups, the task switch was measured, and it was as well measured using the Cortex-M4 and M7 that guarantees that the floating point registers are stored in the TCB and restored. So, for measuring such time, we used the GPIO pins. So there are GPIO outputs and event output. And we used these pins as output, and could see that when the PB6, okay, or to reset and set the PB6, we could use these functions. If we want to see a pure glitch, so pure one CPU tick output, we can use the send event assembly instruction. So this as well differentiates, because such function will delay the context switch by at least 5 to 6 clock cycles. This is a 1 clock cycle instruction. And when we run the microcontroller with a 4 MHz SysTick, we can see the time when one task was finished and the other was entered. So by implementing this, we can measure the time, and we can see that the beginning of the SysTick and the beginning of the user task code took 65 microseconds. Now if you take 65 microseconds and we multiply by the system clock running at 4 MHz, we can assume how long the task switch is. It's 4 times 65 microseconds. 4 cycles per microsecond multiplied by 65 microseconds. And we can as well see a beginning of pend SV and the user task code. So this is where we do the yield, for example, and change or generate the task switch as quickly as possible, avoiding the SysTick. So in this case, the task switch took 37 microseconds. So this is the time generating context switch by a SysTick. This is a context switch by OS yield. So you see there is a difference, which is the source of the context switch. And if we use the combine method, beginning of SysTick and jump to the pend SV, 30 microseconds. That's time that's spent in the SysTick interrupt. And we can as well see jump to the user task within pend SV and user task code. So in this case, 5 microseconds. Now looking at the possibility of generating pulses with an instruction, the SEV send event generates just 1 clock worth of output. But the advantage of such instruction is no other time spent. So now let's speak about the stack pointers. The Cortex-M architecture offers 2 stack pointers that are banked. Both of them are present as a register R13, and the switch between them proceeds automatically. If you run in a dual stack model, that's a initial setup of the FreeRTOS, the main stack pointer is used when you are in an interrupt or exception model. The process stack pointer, however, is used whenever you run a standard application code. So if you are out of all interrupts. The advantage is that it allows separation of the core of the RTOS, which is pointed by the main stack pointer, from different tasks which are pointed by a process stack pointer. So the stacks are independent, and it minimizes the risk of overwriting the main stack for the core of the operating system. The dual stack model has to be switched on, and it is the option for the FreeRTOS. Normally, when you boot the STM32, it starts with a single stack model, so only the MSP is used, both for the standard application and the interrupts. But by turning on the dual stack, then the two stacks will appear. Now let's jump to the API of creating of the tasks. So we can see how the task can be defined and then how it can be created. The task is defined by a macro OS_thread_def. Here we put the name of the handler, the function that will be called when the task is instantiated, the priority, number of instances which is ignored right now, and the number of the stack size currently in bytes. So the CMSys API differs from the native API by definition of the stack size in bytes. I'd like to point out that this is a macro that creates a structure as a local variable with this name. So it adds some prefix and suffix and uses the task1 as the principal name of this structure. Further, when you want to create the task and instantiate it in the heap and put it into the scheduler, you call a function OS_thread_create. Now you can see that the task1 is wrapped by a macro OS_thread, which takes the task1, adds the prefix and the pointer. So effectively it passes the pointer to the local variable created in the OS_thread_def. And the second parameter is the initialization value passed to the task when you create it. The creation of the task will return a thread ID, and you can store it in a handle that can be used when calling a thread-related functions. So if you want to get the state of the thread, if you want to suspend the thread, you need the handle to the thread, to the task. And that's exactly what you get when you call the OS_thread_create. We can, or we should check the return value, because if it is not null, the thread creation was successful. But if it is null, there was an error. Typically, it would mean that there is not enough memory in the heap to allocate the TCB and stack. So in such case, if you didn't implement the hook functionality, you know that there is a serious error and you can't use this thread. You can still operate your application, but this task wasn't created. Now, the task1 handle has got the type of OS_thread_ID. It is created with this function, with the definition of the thread created by the macro and an argument. You can as well terminate the thread by calling this function with a thread ID. You can as well pass null to delete a current thread. So if you want to terminate yourself, you pass a null or 0, and that will find the appropriate value automatically and terminate the current process. You can get the task ID by calling the thread getID function. So if you need it for other purposes, you can as well obtain it. How to control the behavior of the task? When you are within a task, you can yield. This means the thread at the current moment will be interrupted and it will cause a task switch. So if another task is waiting, the yield will cause the other task to run. It's a very effective method of not wasting the CPU time if my job is finished. So I don't spend time drinking coffee. I give the microphone to my colleague immediately. That's yielding. You can test if a thread was suspended by calling a thread is suspended with its ID, and it will return whether the thread was put into the suspend state or whether it's in other blocked ready running. You can resume a suspended task. You can check the state of the task, so you can detect whether the task is ready, blocked, suspended. You can as well resume and suspend all tasks. This is very useful when you want to stop the execution of everything and you, for example, wait for an interrupt to resume. So if you want a lower power mode, you can stop everything and, for example, on a button press, that will resume all tasks. You again return to the functionality.